We're almost ready to go. After hearing from our alumni, basically we wanted to have a session that showcases the research work that is actually going on currently in the department and outlines the pathway for the future of the department. And we are going to have 6 representatives from the academic body of the department representing the 6 research areas that we have active in our department. So we are going to start with Professor Marc-Olivier Coppens talking about nature-inspired chemical engineering. So the stage is yours.
Thank you very much, Matteo, and it's such a pleasure to be here to celebrate the centenary with you. So I'm going to say something about nature-inspired chemical engineering. First of all, what that is, why we do this, and the breadth of the research we do in the department on this. So where we start off is grand challenges. I mean, we have a lot of crises to solve. I mean, these are, you know, about UN Sustainable Development Goals, but at the same time, we have economics and industrial strategy. And how do we solve all these issues together? Because that's the big question. We can reformulate these all the time, but the question is, how do we have what's really needed, which is transformative change, rather than some incremental changes? And so we really need some disruptive way to change, because this is a picture here of a so-called modern chemical plant today, and here I take one from the 16th century. And you see some vessels in series, and maybe the ones on the left they are in wood, and one on the metal on the right, and maybe computation and so forth has advanced, but has our thinking really progressed? And the question here we pose is, can we innovate by drawing lessons from nature? And we've been researching this here at UCL through nature-inspired chemical engineering, but also to a very interdisciplinary center for nature-inspired engineering, founded now exactly 10 years ago, started with funding from the EPSRC, a £5 million grant, with lots of support from various industries. So I'll say a little bit more about this. There are also reactors all around us. Trees are also chemical reactors. They solve one of the most challenging problems in chemical engineering of scalability and effectiveness. And so all the scales also matter. We need to think in a much more holistic way. The chemistry at an nano scale, but the structure of the leaves, the trees, all of this is necessary for this tree to be able to grow. And so nature-inspired chemical engineering is learning from this, is learning from the architecture and dynamics of natural systems at all scales to help us design, synthesize innovative solutions, more superior solutions to various technological challenges. But still, we need a how. We can't just say, okay, we're inspired on one day and not on another. We may need a methodology. So we need to first think about mechanisms and fundamentals, and that's core to us. You know, it's scientific basis of engineering. And also appreciate that the context of a tree may not be the same of a chemical reactor in terms of timescales that we need of products, the energy, the temperatures, the pressures, and what more. And of course, there's the social, economic context and so more. A second is that we need really a methodology, and we've developed at our center a systematic nature-inspired solution methodology that is centered around different themes that are related to particular mechanisms that are at the heart of effective properties like resilience, like adaptability, scalability, and efficiency in nature. And so this methodology, I can't go into the details of it, but it really relates what you see in, for example, trying to solve the scalability in a chemical reactor such as fluidized beds, and several of you have visited some of the labs downstairs and saw them again, and say, well, you know, it's difficult to scale, the hydrodynamics are complex, but we need the mixing properties. How do you learn them from trees and lungs and vascular networks? Have the scalability that you can uniformly distribute fluids from one point to many. That's what we use here. We use this abstract concept and then integrate it within this fluidized bed reactor to very uniformly distribute the fluid over it, and in this way much more uniformly distribute, have better heat transfer, have higher selectivities and yields towards the products we want, and operate processes in a scalable and safer way. We apply this also to fuel cells, like lung-inspired fuel cells, because one of the issues with hydrogen fuel cells is the distribution of the air at the cathode, and also the scalability of them, and the expensive metals like platinum often used in these devices. And so we can learn from trees, but also from lungs, with a similar hierarchical fractal self-similar structure, looking the same at multiple scales, and we designed the flow plates to very uniformly distribute the air over this fuel cell, and then very effectively distribute the catalyst, like is happening in leaves, but also use the fact that in the lung, there's a minimum of metabolic energy that's used through food for breathing. The energy is used more for walking around and for our brains. And we use these type of concepts to redesign fuel sets, and then we can print some of these using and with selective laser sintering, and in fact with the X-ray microtomography, which some of you have also seen downstairs, we can actually kind of visualize this process as well, and demonstrate that we have this much higher current densities and power by this lung-inspired process. So this is a very complex diagram, but it shows that we use the same type of systematic design methodology to link a practical problem with one from nature, stepwise, to design, and then iteration to make it cheaper, like using, for example, printed circuit boards, which was in the thesis, for example, of Sasank, who is here with us today, who did his PhD on this topic. And now we're kind of expanding this further to electrocatalytic devices for CO2 electroreduction and for electrolysis, for hydrogen, which is interesting in an industrial project with Total. And again, we need to take this holistic approach, looking at all scales to be able to do that. But there's more than trees. Trees are part of a system. They're part of a forest. And we look at ecosystems such as trees to think about, well, net zero manufacturing. That's what forests need to be able to do. And so what's better than to look at this? And here there's a project that is led by a colleague, Massimiliano Materazzi, where we collaborate in an EPSRC project with several industrial partners to think about how we can learn from the cycles of trees and how we can link about this hierarchical structuring and pulsation and dynamics that we see in nature to look at the very practical problem of distributed manufacturing of olefins on the base of synthesis gas in one step rather than multiple steps where the syngas can come from waste or from biomass. And this type of approach is one that we're investigating together, so it shows how we really integrate things. We're looking at problems of antimicrobial resistance as well, which was done by a first undergraduate, Halan Mohammed, who then did her PhD with us, who was looking at membranes inspired by the kidney, and the kidney that can separate and do water treatment, in fact, in our bodies without fouling, and it has to do this for a lifetime. So that relates to the structure that you see of these brush-like structures with that are hydrophilic and have charges on them and can repel foulants. And that type of principles was used then to look at water treatment, but in integration with another PhD student working in the group, working on gold nanoparticles for catalytic properties and for oxidation reactions. This was integrated by them. This was a project they came up with themselves as PhD students in their final years, working together and thinking we could use this for antimicrobial resistance, and then worked with someone in UCL hospital to look at this. And this can kill bacteria. Obviously, I can only give you a snapshot of this because of the time we have, but there's a variety of applications of accelerated innovation we can have in our center on a variety of topics where some of our research has gone to space, so nature-inspired multifunctional surfaces, some work on cancer immunotherapy, working on the Cancer Grand Challenge. Some of you have seen Matthew's work in the lab earlier, dental materials that we have now just licensed last year, and so forth, and various type of applications that this approach can lead you to. So this has involved many industrial partners and philanthropic support to make this possible. Now, apart from that, we actually are more than just a few groups, but we, as a center, we've given funding to early career researchers for short research of 4 to 12 months, mostly led by early career researchers in a whole other fields, to also work together with researchers from other universities or other parts of UCL and look at a whole breadth of different topics where they can seek inspiration of nature. And I indicate in yellow those led by, at that moment, early career researchers here in our department. Some became full professors in the meantime. And so I cannot go into all the details of them, but some are actually reflected on posters outside. There's, for example, learning from the pulsed blood flow and how you could, in micro and microfluidic systems and millifluidic systems, change the profile by pulsation and by having a coil system, and in this way make nanoparticles with, by controlling beta to resonance time distribution. By Luca Mazzei and Asterios Gavrilidis, who worked with colleagues in Strathclyde. Max Bazenhart at that moment, his first grant, and is now a lecturer with us at the Manufacturing Futures Lab, who looked at bio-inspired molecules, thinking about magnetostatic bacteria, where you have these particles lining up in bacteria with magnetic properties. How can you learn from these properties, having bio-inspired proteins molecules inspired by these proteins that can actually control the crystal structure and alignment of nanocrystals? And then we have Pickering emulsions, which are very important in food industries, but also in drug delivery, which Jota and with Yang Lan has been working on, a postdoc, Simona Migliozzi, in our department, working together with pharmacy, and they got inspired by force balancing you have in various plants, and learning from that and how you can make these microgel particles here, so droplets with microgel properties, where depending on the environment and the balancing of forces, you have completely different rheological properties they can use for transdermal delivery. So very exciting work that's led to a variety of other grants after this and further projects and collaborations. Yang Yan in our center is doing some amazing work over the last years. It's very relevant if you think in the context of CO2 and water. And I just want to highlight one project here on stoma, inspired to the stomata in leaves that you have for the breathing of the leaves and the capturing of the CO2, and to do CO2 separation. And his team, this leaf tech team, won a top prize from the London Business School and are starting a business on the basis of this idea of CO2 separation membrane technology. And so there's plenty more that he's doing on CO2 reduction and things. I want to point you to the posters later and speak with them. Diego Lopez Barrero, some of you have seen him at UCL East giving the tours, and is a bright new lecturer on nature-inspired solutions. And he's looking at the engineering of nature-inspired recombinant proteins and making all kinds of new materials of this with controlled functionalities. You see here incorporating living cells to make engineered living materials, something he just got a prestigious new grant on as well. So this is going to be some very exciting new directions for the center, using the capability of the manufacturing future labs that we have seen at UCL East. So what I've tried to illustrate is we can take inspiration even from our garden, but we need a methodology to link a real application we want to solve to the aspects we have in nature. There's so much to learn from nature to try to reach sustainability, and we really need to do that back because there's a lot to learn, but you need the tools of engineering and science to make that link. And actually that's something we teach, and for 9 years I've been teaching the nature-inspired chemical engineering module to final year undergraduate students and master's student chemical process engineering. And now we've related this to a program on the MSc on nature-inspired solutions taught by these various people at UCL East, and that has an intake from students with various backgrounds, thinking in an interdisciplinary way how they can solve challenging problems, how they can innovate by drawing lessons from nature. How do you actually do this? And this is very much project-based. So thank you very much.
Thanks, Dr. Leo. Our next academic is Dr. Marcello Sega, that joined the department as an associate professor, and the stage is yours.
Thank you, Matteo. So I will try to give you an idea, an overview of what our department is doing in terms of research in molecular thermodynamics. Now, you know that one of the most interesting things of chemical engineering is that it spans scales in a very broad range. Now, molecular thermodynamics focuses on the lower end of the spectrum and combines methods and principles from quantum chemistry, statistical mechanics, and transport theory to try to link the properties of matter at the microscopic scale to what we know and what we experience on the macroscopic scale. Now, we are doing this to measure properties like absorption, phase equilibria, crystallization, and these are some of the topics that are covered by our staff using methods of molecular engineering thermodynamics. Now, I will select some of the themes, some of our research themes, and I would like to start with the work of Matteo, who is trying to change what is the conventional computational approach in pharmaceutical manufacturing, which is based on a purely thermodynamic paradigm, where it says that thermodynamic stability is a proxy to synthesizability. Now, under process condition, this is not true anymore. Kinetics, out of equilibrium effects are very important. And in particular, when you start forming different polymers of crystals, the molecular scale effects are very important because they are amplified at the level of the whole crystal due to the long-range order. And he does this and predicts crystal nucleation using molecular simulation aided by machine learning techniques. And this is to aiming at getting more affordable, safer, active pharmaceutical ingredients and novel formulations. Now, this is a fully computational approach, but as you've seen before, there are also, these methods also going hand in hand with experimental approaches, this work of the group of Marc Olivier. We've seen some of this before when he uses nature-inspired principle to study hierarchical structure porous catalysts, for example. And in this case, there is a weave of theory, simulations, and experiments that try to understand what are the origins for observed barriers in the diffusion of chemicals in this crystalline structure. And they discovered that the presence of interfaces within this crystal are quenching very much the diffusivity and then the activity of this catalyst. So molecular simulations here are really helpful to understand this, and we know that interfaces play a very important role at the microscopic level. And this brings me to my topic, which is studying interfaces between fluids or between liquids. And even if you have a molecularly or atomistically precise model of your system, it might be very difficult to understand what happens really there at the interface. Because in the case of liquids, you have typically thermally activated surface mode, which are capillary waves, and they kind of blur the picture. It's like looking at something and not being really able to focus. And you see this structure, which is kind of blurring the density profiles of these liquids. Now, I developed algorithms that are trying to undo this mirroring effect and give us a more focused picture of what is actually the structure of a liquid-liquid interface. You see how much crisper it looks like when you're able to remove these effects. And we are applying this not just to the structural properties of fluids, but also to the transport properties. So if you are able, with these techniques, to select the very uppermost layer, the very first uppermost molecular layer in liquids, and study, for example, their diffusion, which can be magnified by a factor of 2, 3, 4 times with respect to the bulk. And this has also a similar effect in terms of transport of momentum and of the viscosity. You can measure now the viscosity of the interfacial layer and find that it has a broad, largely reduced surface viscosity. And as you can imagine, this can have an impact on surface reaction, with implication for environmental chemistry, reaction of aerosols, surface of pre-melted ice, and so on. Which brings me to another topic, which is about interfaces, this time interface between solid and gas, and it's the work on metallo-organic frameworks from Peyman. General metallo-organic frameworks are nanoporous material, which is synthesized from some molecular building block, which are very important for sensing, energy storage and conversion, carbon capture and separation. And you see here in this plot, in recent year, our capabilities in terms of ab initio quantum mechanical calculation are being greatly increased, and we can reproduce almost exactly the experimental results. And this opens a lot of avenues for conducting our research in a completely different way, fully digitized if you want. And this is what Peyman is also doing by integrating quantum chemical calculation with data science, and has a model, a package to compute, to perform computational screening and material discovery from harvesting databases and doing also quantum mechanical calculations. Another very important porous material is the one which is studied, the class which are studied by Osgur, and this is about also some application which are important for our environment and for keeping our environment clean. And it's about this molecule which are pairing polyfluoroalkyl substances known as PFAS. You might have heard of them. They have been basically introduced in the 50s. They are now being phased out, but they are still found basically everywhere because they are very hard to degrade and to remove. And the simulation work of Osgur are helping finding and identifying new porous material which are very apt at capturing this type of chemicals. Now, I talked a lot about computer simulation works and theory. There are, of course, several experimental investigations going on in our department. You've seen something about this already. Yang Lang is using microgel to study or to create new responsive type of emulsions. The typical stabilization approaches, for example, with surfactants or with solid particles in the case of Pickering emulsion, have, in this case, a fixed contact angle, as you see, of the particle which is absorbing at the interface between the two fluids. And instead, if you're using molecules like this one, you see here a trimer of Knightman. If you have a longer chain, this basically creates a polymer which is coordinating a lot of water at low temperature. And when you raise the temperature, this molecule basically squeezes out all the solvent and changes its shapes and size. And so you can gain a very precise control, for example, on droplet size distribution, and then on the rheology that can move from gel-like to plastic solid. The fact that you can use the molecular detail to obtain whatever type of tuned material you want is nicely shown in this example of the research of Stefan. And he uses, for example, block copolymers that can self-assemble and create some nanoblocks that you see above there that are used as a substrate to grow, for example, gold nano islands on which a series of molecules and receptors are placed. This can be used to create self-assembled nanostructure array that can amplify the detection of extracellular vesicles, which are one of the means of the cell to communicate with other cells and transport also material between each other. Last example I wanted to show is one of the latest work of Ryan, who's working on the cerium oxide, which is a very particular material, has an excellent oxygen storage capacity. And this happens because this lattice that you see here can host a lot of vacancies. These vacancies are created by the removal of oxygen. And it was always a puzzle why this lattice can be so stable in presence of so many vacancies. And actually using a very interesting technique, which is the resonant inelastic X-ray scattering, managed to show that actually the presence of a vacancy means so induces a strengthening of the bonds in the neighboring region. And this was possible to study using some in situ very precise measurement that you show here. So I'm coming to the end of my presentation. I basically hope I managed to convince you that molecular level of understanding of the system is very important to be able to understand what happens at the macroscopic scale, to tune our system, and has some very fundamental but also applied aspects that are helpful for problems in energy storage, environmental and pharmaceutical applications as well. Thank you.
Thank you so much, Marcello. Next, we have Professor Panagiotou Angeli that's going to talk about multi-phase flow.
Thank you. So this is back and forth, isn't it? Yeah. Okay. So it's a pleasure to be here this afternoon and welcome everybody from my side as well. It's actually fascinating listening to my colleagues because one of the things I was going to say is that we are actually very multidisciplinary and interdisciplinary. As I'll show you in my talk as well, there are a lot of overlaps. And I also discovered that I should talk to my colleague about one particular research area. So it's a good day. So multi-phase systems. I try to put a mission statement here. What are we doing as a research area, theme in the department? We heard very nicely in the previous talks that flows, that's what chemical engineering is, isn't it? Where's the and especially multi-phase flows. So what we try to do in the multi-phase systems area is to study the flow, the phase interactions, and the transport properties of multi-phase mixtures. And we combine advanced experimental techniques I think some of you had the opportunity to see some of these advanced experiments we are doing in our labs in the basement, but also modeling and simulations. And we go across the scales from micro to pilot scale. And of course, our aim, as with a lot of the other research areas, is to support development of sustainable processes and green energy technologies, which are essential for transition to net zero and to a circular economy. And I should say that we are embracing machine learning and artificial intelligence approaches to improve predictions, but also to aid the digitization of these processes. And as I said, we have a lot of collaborative work across between ourselves within the department, but across universities and industries. So I will present you here the work, some highlights of the work of some of my colleagues. I was trying to find a way to follow that logically, and I think what I'm doing is I'm going across the scales in a way. And I'm starting here with Stefan, and you've heard something about his work before. So he wants to see how materials form and interact on the nanoscale, and he uses as building blocks, he himself and his group, polymers, nanoparticles, and they try to create colloids and interfaces. So one highlight of the work they've been doing is this development of the point-of-care microfluidic device for drugs, for chemotherapeutic, that can quantify drugs from very small bodily fluid samples. And you can see here, this is a large European project actually, and you can see here on the slides, and I don't know if that is going to play again, but the publication and how the microfluidic device behaves. Moving slightly, this is healthcare applications, it's not all about energy, but moving slightly up the scales, we have the work by Luca, who is doing a lot of modeling, either in as theoretical modeling or simulations, but also tries to confirm, validate these results with experiments to gain some fundamental understanding, especially of fluid particle systems. And a representative project is shown here, which is to predict the rheology of particulate suspensions. The application they had in mind was these wash codes that are used for developing catalytic converters. You have to, catalytic converters are used to control the gas emissions, exhaust emissions. And this wash code is suspension of particles in ionic solutions and aqueous ionic solutions. So when this wash code is applied, you have to make sure that it is applied uniformly and you maximize the area, so the catalyst, the area of the catalyst. In a way to do that, you really need to see how to apply the wash code. You really need to understand the rheology of it. So that's the projects they had been working on, to predict the viscosity, to validate against results from rheological measurements. And effectively, once they can understand and predict, they can scale up the approach for the wash code, the application of the wash code suspensions. It's a project funded by Johnson Matthey. So I am in between, across the scales in a way, and so myself, I'm also trying within my group to understand the fundamentals of complex multi-phase flows and the applications to sustainable processing, and particularly looking into two-phase flows involving liquids. And an example of the application I'm showing you here is the recycling of critical metals. We've heard a lot about renewable technologies. A lot of them use all these critical and rare earth metals. Of course, these metals also appear a lot in electronic waste. Some example of electronic waste on your right here. So it is important for various reasons, for availability, security of supply, but also for environmental concerns related to mining, to try to recover the critical metals from these technological electronic waste. And what we do is that we develop small channel intensified processes to recover the metals. So some examples of the small channels on the very left. We are doing experiments and simulations to try to understand them, and then we work on the scale up of these systems. I should add here that this work is supported by Johnson Matthey, but also by the research, the UKRI and European projects. And one of the things we've been looking generally in this space of predicting multi-phase flows is to see if we can not only use physics-based models, but also data-driven models to improve the prediction. And I don't know. Ah, there you are. Can I go back?
It's a little bit.
Very good. Yeah. I think I didn't. Ah, there we are. Okay. Marc-Olivier, sorry, it's a repeat of a slide, but from a different angle. So, yeah, as Marc-Olivier explained very nicely, they are using nature-inspired approaches to predict, but also to improve, intensify the processes, the chemical processes. And the example I have used here is the one where, based on inspired by nature and the fractal branching of trees, they developed this injector in a fluidized bed, and you see here the design, but also the way they used additive manufacturing to make it, and of course that enables the uniform gas distribution in a fluidized bed and can lead to very nice results based on conversion. And as Marc-Olivier also explained, another way they've been looking, and their approach they've been looking, is this to have dynamic structuring within the fluidized bed using pulsation. Massimiliano, we are going up the scales now. So Massimiliano, you probably visited, or some of you have visited also the fluidization lab downstairs in the basement. They, himself and the group investigate novel reactor configurations, catalyst multi-phase systems for efficient waste conversion into hydrogen or sustainable fuels. And there are two projects here, examples of two projects that have been involved, funded by, this one is from the Department of Energy Security and Net Zero, and by a company. One is for waste gasification. I think some of you also saw samples of this waste outside the lab, or the multi-component reactors for carbon capture and production of hydrogen. And this actually system is going to go to pilot scale, and I think there would be a pilot plant as well in MFL in UCL East. So the Harun is working on, and his group are working on CO2 problems, carbon encompassing carbon capture, transport, utilization, and storage. Harun has been quite successful, actually, or very successful with European projects. We see here all the successful projects over the years. One large part of their work is on CO2 pipeline transport safety and operability, where they've developed mathematical models to predict what happens if pipes erupt. And also, you see here on the right an example of carbon capture and sequestration development for the iron and steel sector. These are European projects involving various partners and pilot plans to demonstrate the approach. And going even bigger on scales, we have a lot of work in the department actually on life cycle assessment led by Paola Lettieri and more recently Andrea Paolillo. So the Paola and Andrea have been working in collaboration with industry, NGOs, charities and government, and they apply this life cycle assessment approach to various different projects. A lot of them are for process industries, but the example I have put here actually is from a project they did for the recycling. Well, a project they did together with the Royal British Legion about the recycling of the poppies that are manufactured every year to commemorate the Remembrance Day. So they investigated the life cycle of these poppies, and they actually found that by using recycled coffee cups, they could actually improve the sustainability by 40%, I think, the environmental sustainability of this approach. So this is the highlights, some of the highlights. This is the next one, okay, sorry, that's the next group. But these are the highlights from our group, from multi-phase systems.
very much. I'm Ryan Wang, and I'm representing the Catalysis and the Reaction Engineering Group. I'm very nervous because the last time I presented a slide in front of all my colleagues was 9 years ago. I'm doing the interview. And then I want to ask you some questions. How many of you still remember that you did a module with us called the Chemical Reaction Engineering? Raise your hand. Okay, the next question will be more difficult, huh? There are two reaction equations. There are two equations very important there. The first one is called rate equation. Do you remember rate equation? Minus R equals to K times C, and there's a power of alpha or something, huh? That's called the rate equation. The second equation called design equation of the reactors that describe the conversion as a function of the reactor sizing, so we know what type of reactor and how big the reactor it is. Do you still remember? Raise your hand if you still remember that. And that, these two equations is what we are working on. For the first one, we're trying to increase or optimize K, and then we can get a much better rate. And then once we get a much better rate, we're trying to reduce the volume of the reactor, that reduce our carbon footprint. So our mission is to convert green energy to chemicals. On the left-hand side, what we are doing, this is the modern life oil refinery or the chemical industry. What we are doing here is by improving the K and also reducing the V, we are developing new catalytic materials or new oil and gas process that can achieve much better production yield with much smaller carbon footprint. On the right-hand side, it's something that does not exist in the industry. What we want to do is to get the renewable energy, that is from solar and wind, and then we get either the light or the electrons, and then we are using light and the electrons to drive chemical reaction to convert CO2, water, and the nitrogen into synthetic fuels that we can do the transportation industry or fertilizers for agriculture industry, agricultural sectors, and new materials as well as functional chemicals for pharma industry. Here, we are developing materials, catalysts, to improve the reaction rate, but we are also developing process on the bigger scale because those processes are not there, that not existing there. So we need a lot of chemical engineering, new chemical engineering that is not taught in these chemical reaction engineering modules to be able to make these e-refineries. I try to plot everybody, we have over 10 academics working in the areas, as two functions. The x-axis is the dimension we are working on. We start with nanometer, which is 10 to the minus 9 meters. That is working with the small molecules, how the molecular interactions. This may not be 100% absolute correct, but because otherwise I will put everybody in a big circle. So I just want to slightly differentiate everybody. And then on the y-axis is where the energy input. We have the traditional heterogeneous catalysis where we need the heat reactions, or we are using electrons and photons to drive the reaction. I will start with Yang and Stefan. And for example, what Yang is doing is trying to develop new catalyst to convert solar energy into the energy stored in chemicals. And they are also trying to develop processes that can make it into a bigger scale. Tom Miller and Rod Jervis, what they are doing, and also other EIL people we'll see later on, is trying to using electrons to drive reaction. This can be for the case of reducing the CO2, and also can be used the thermal energy from the electricity to make hydrogen. What I'm doing here is basically on the fundamentals of a bond breaking process and bond forming processes in electrochemistry and the catalysis. Asterios and Federico, what they are doing is trying to use automatic reaction engineering to develop reaction models. And my colleague there, of course, also works here, but works more on the design of nature-inspired reactors as well as the new catalytic reactions. George Manos is working on how to use catalysts to decompose polymers. And finally, Max and also Maximiano, they are working on slightly bigger processes, and as one of the reactors that Jutta just showed you. The research happens here also are supported by a lot of industries. And it's also quite important to see that the industry is not only interested in the bigger processes, but also invest into us into small scales to try to understand the fundamentals. And our industrial partners are listed here, at least provide a cash contribution to our projects. And you can see they are not only UK-based companies such as Johnson Matthey, but we also have partners globally. We have Toyota and Horriba from Japan, and also we have the Honeywell and from US and BSL from Germany and many other companies. Okay, so I will try to give you a very short demonstration of some of the key innovations we have that are very different from all the other chemical engineering departments. So everybody knows how to make a photocatalyst. You have a semiconductor there, and they absorb light, and you split water. That's very easy. But what is difficult is to make a reactor that can efficiently absorb the light. And for example, this reaction is by producing hydrogen from water and ethanol, and at the same time also produce acetic acid, which is a very important chemical. And it's important to engineer in the way that we can absorb both the visible and IR light. And they also at the same time facilitate the separation of the products. That requires a lot of engineering input into these photo-electro-catalytic reactors. The next example is by our people from the electrochemical innovation labs. And here there are several reactions going on. So for example, we can use the electricity to split water and make hydrogen. That means that we are stored energy from hydrogen. And we can also then convert hydrogen back into water, and that releases the electricity. We call them fuel cell. And that's basically we can drive a fuel cell cars, or we can have the fuel cell storage for the grid storage. Or we can also use the electricity to reduce CO2 to make chemicals, and also use electricity to reduce ammonia, or to reduce nitrogen to make ammonia, and that ammonia will come back into the fertilizers. And what we're showing here is that we not only doing research on the fundamental scale to make this nanocatalyst in a size of only 1 to 10 nanometers, but we assemble them into a very big MEA sheet that is usually 5 centimeters by 5 centimeters, and we pack them into a fuel cell, and then we can have the device performance. So we are in the engineering department. We can come all the way from a small-scale nano-catalyst that we can't see that with the naked eyes, but to make it all the way into a device that can produce electricity. And here is an example from Mark Oliver. Here they are using a gold catalyst for a very important reaction, which is the propylene EPO oxidation. It's not possible in industry to do this reaction with molecular oxygen. In industry, people are using very expensive hydroxide species that basically increase the price of this propylene oxide, which serves as a very nice precursor for polymers, but also for fine chemicals. And Mark Oliver, for the first time, is able to design a gold in zeolite catalyst that is able to use molecular oxygen, that you can see that achieve very nice rate of the reaction, which is showing here. Again, this is also starting from a very small scale. The catalyst is only about 0.8 nanometers. And that is very, very small. And then all the way to the reactor size of almost a meter. And you can see the production rate, which is a gram of the propylene oxide per hour per kilogram of the catalyst. And this can then be scaling up into a pilot scale and then applied to the industry. That also means that we are tackle the problems in a very multi-dimensional way. So for example, here's a typical catalytic reactors or catalytic converter that if you drive a gasoline car, then you will have that. And then this is already in the dimension of here, but we can tackle the problems all the way to the nanometer scale where the catalysis is taking place. And this is also a multi-scale problem for the time. For example, usually we have a reaction that takes place in a second or a millisecond. But we also have these intermediate species, short-lived intermediate species. Their lifetime is only in the orders of nanoseconds to microseconds, so 10 to the minus 9 seconds. And fundamentally, we have a bound breaking process, bound formation process that in the range of 10 to the minus 12 or 15 seconds. We, as a department, as a section here, we have all the characterization tools that can tackle all the time scale here and also all the line scale here. I will give you an example, which is what we are doing is that we usually, when we measure kinetics, we get the whole reaction conversion kinetics, which is in the black box. Up till now, it's impossible to understand what is the kinetics within a reaction or within a very single bound breaking process. In the past few years, we, as a department, has been able to improve that. So now we can measure the kinetics in the red box and comparing that to the kinetics in the black box. So from that, we can differentiate what is a rate determining step. And finally, the final case is that not only we can understand the kinetics in the very small scales, we can also make these autonomous reactor platforms for kinetic model identifications to build more accurate kinetic models, and that's the work from Esteemed and from Federico. What they do is that they use a cloud-based systems, and from that they can guide how to precisely measure kinetics in the experiment. And driving the kinetic data, then they can do identification of key models and using machine learning methods to optimize the models. And then finally, they can feed back to the real manufacturing. And with that, thank you very much. And then.
Thank you so much. So our next speaker is Dr. Vasilis Karitopoulos.
Well, hi everyone. Thank you for joining. A warm welcome from me as well. My name is Dr. Vasilis Karitopoulos. I'm a lecturer in the Products and Process Systems Engineering Group. And the next 40 slides are slow. We will try to answer the question, what is process systems? No, we're not going to do this. We're already late. So we're a group of 10 or so academics, and a quick recap over the last decade in terms of numbers. We've been very prolific in terms of research output, both in terms of publications, but also in terms of strategic involvement in the funding landscape, with one prosperity partnership through UCL, Imperial, and LI Lilly, our involvement in 3 program grants, and 1 international center-to-center grant between UCL, Imperial, and Aachen. Here we have an unknown acronym, that's CPSC, that's for the center at Imperial, to which we're also part of. It was inaugurated in the early 90s by Professor Roger Sargent. And the idea is that we are a multidisciplinary group with chemical engineering, mathematics, physics, chemistry, and computer science. Our application domains and competence areas range across all sorts of scales, from molecular design all the way to supply chains. And in the convention that was established in the previous speakers, I will also keep on abusing time scales and length scales. So we're dealing with multi-scale modeling and systems thinking, and our approach is how do we design and operate systems that are already established, so we draw lessons from that, to the new kind of paradigm. We want systems to be agile, reconfigurable, and also sustainable. So, a very familiar picture. We start from molecules and molecular clusters, and here we have the work from the group of Dr. Lee with computer-aided molecular design together with machine learning, trying to answer the question, when you want to design a process, how do you do this holistically, from the selection of the appropriate, let's say, solvent to the design of the equipment itself. And we also have work from the group of Professor Dua with the modeling of gene delivery in patients with hemophilia type B, but also the model-based control of non-viral sRNA. So you can see here the application domain varies widely, but the underlying principles are the same, as it will be revealed in a bit. So then we move on to films and multi-phase systems. Here we have examples of work from the group of Professor Sorensen, Professor Matsai, and Dr. Bezenhart. This is part of the Prosperity Partnership grant I mentioned before. They study HPLC systems, so they start from molecular descriptors with limited experimentation and the use of machine learning to develop a digital twin, so as to, at the very end, optimize the superstructure of the chromatographic separation process. So we start from the low scales, and we take it all the way to the superstructure of the system. And as we already heard before, we have from the group of Dr. Galvanin, the autonomous reactor, where basically you can optimize the operation of microreactor systems through the use of mathematical modeling and machine learning with no human intervention. Moving on, we deal with process units. So here we have work from the group of Professor Sorensen, studying the optimization of complex distillation process, ranging from the conventional one all the way to cutting-edge types of distillations with reactive, hybrid, and divided wall column, and again from the group of Dr. Galvanin in terms of the physics-informed machine learning optimization of reaction systems. Now, these are sort of the two most typical unit operations we see in the chemical engineering. However, we can take the same paradigm, the same analysis, and we can apply this to other applications. So here we have the work of Professor Bogle in terms of the modeling of the lever function. So you can see the lever as a reactor, and you can basically optimize and monitor its operation. And from the group of Dr. Galvanin in terms of the diagnosis and the optimization of dosage for the von Willebrand disease. Next, once you have your process units, you have your plant and your system. So here we have example of work from the group of Professor Eric Fraga on the thermal power generation from nuclear fusion, this in collaboration with the UK AEA. And again, once you have the flow sheet, you have designed your equipment, you have designed the system that you need, then you want to see how this looks like in actual space. So then we jump to the group of Professor Papageorgiou for the optimal layout of multi-floor process plants. You have the sizing of your equipment, you want to minimize the footprint of your manufacturer, so you cue the optimization to give you what is the layout that is appropriate. Now, once you have your plant and you're an enterprise, you want to optimize your operation across all the scales. So you want to study in an integrated manner the integration of planning, scheduling, and control. So work from my group, we study the data-driven integration of tactical planning with the operations. How do you coordinate the demand allocation across the different production centers that you have, and at the same time make sure that the plans that you dictate to your individual plants remain operable. And by the same token, we move from the process industries to the energy systems. Optimal microgrid operation. You can think of the microgrid as a number of buildings where they have their own infrastructure in terms of energy storage and perhaps renewable energy and thermal generation. And this system aims to increase its profitability through its interaction with the main grid. So they're bidding in the day-ahead market. So you study the system and you can make decisions in terms of how do you handle the demand, how do you charge or discharge your batteries, and when do you bid and how much do you bid. At the top of the list we have the supply chains, and again work from the group of Professor Papageorgiou. We have the integrated planning of industrial gas supply chains when you take into consideration the different manufacturing sites across different spatial and temporal scales, so you optimize at the same time the planning and the distribution through the consideration of delivery to customers, so the vehicle, the also known vehicle routing problem. Or again, moving back to the energy systems, we look at the optimal decarbonization pathways using multiple vectors. I'm involved in this area as well, so we're looking at industrial heat decarbonization in the race towards net zero, or how do you co-optimize this future multi-vector energy supply chain, including, for example, hydrogen, natural gas, and biomass considerations. And we also have work from the group of Professor Bogle in collaboration with the University of Palermo in the circular economy of water management. So again, the underlying thinking is the following. We have a system, no matter how complex it is, we want to make some decisions, subject to some constraints, and want to make sure that we either minimize cost or optimize the flexibility, the profitability, or the sustainability of the system at hand. These are the systems that we study, and this is half of the work. The other half of the work focuses on the computational optimization and machine learning. So we want to create tools that are efficient and user-friendly enough to be deployed later on. So here we have optimization-based machine learning for explainable AI tools from the group of Professor Papageorgiou, global optimization techniques for hard non-linear problems that we typically face in the chemical engineering from the group of Professor Bogle, nature-inspired optimization techniques from the group of Professor Fraga, and from my group, data-driven optimization techniques to handle uncertainty and risk. How do you look at the data that you have and actually use them to make informed decisions? So, throughout the last 30 years, we had a very fruitful interaction with industrial and partners and policymakers. I think we have the poster session following up, so I'll keep it to that, and I'm very much looking forward to the interaction with you. So, thank you.
Thank you, Vasilis. I think we are up to our last speaker for this session, who's Dr. Alex Retti, who's going to talk about electrochemical engineering.
Ace. Thanks, Matteo, and good afternoon or evening, whichever one it is. But first, before I get into this presentation, maybe another question for the audience. How many of you remember taking an electrochemical module here? Oh, pretty good. Eva, come on now. No, that's great. That's great. You do? Wow. Well, you see. So, everybody then already knows this. I can sit down. No, electrochemical engineering is not a sort of traditional area in chemical engineering, I would say. And when I was an undergraduate, it wasn't even an option to take an electrochemical course. That's not the case anymore, and I would argue that UCL is really at the forefront of introducing electrochemical engineering as a core pillar of chemical engineering, and all of the fantastic things that we've heard so much about today, the tenets of chemical engineering, are just as relevant to fuel cells, electrolysis, and batteries as they are to all of process engineering and other fields that we've already heard about. What the heck? Oh, it's upside down. This is activity at UCL is concentrated between two labs, the Electrochemical Innovation Lab and the Advanced Propulsion Lab. And at the risk of using another diagram that talks about scales, here we go. We go from very small scale activities around basically materials discovery, looking at fundamental reaction mechanisms and the movement of atoms, all the way through to designing, hold on, just going to do it. All right, whatever. Devices here in the middle, all the way up to looking at these at an industrial level and trying to tackle some of the problems that you have when you're trying to engineer large-scale electrochemical systems as well. And I'll start with our first lab, the Electrochemical Innovation Lab, which is actually, I believe, right below us. Some of you may have seen it or maybe even worked in it. So it's down in the basement where all the good work happens at UCL. And it looks a little bit like this. It's quite a infrastructure at the moment with lots of offices and lots of areas for different activities. The bottom line is, if you are interested in working on batteries, hydrogen technologies, supercapacitors, anything that does electrochemistry and maybe even a little bit of nuclear fuel processing, come see us. Right? This is what we do, and we're real experts in this area. We're also very proud of our imaging suite. So this is a Zeiss microscopy suite that goes from different types of X-ray machines where we can image large devices all the way down to the nanoscale and indeed all the way down to sort of angstrom level imaging. This is a unique facility in the world, and when we collaborate with industry, which we do quite a bit, they often come to us for this capability. Right? They want to see inside their devices as they're working in order to understand them better and design them better. In terms of the Electrochemical Innovation Lab, I won't bore you too much with stats, but we do a lot of research. We're heavily involved in the UK's premier battery funding body, the Faraday Institution, and we lead two of those projects, LifeStar and SafeBat here. We work all across the department and we work all across UCL as well. And on this slide here, we have a number of images from that microscopy suite that I mentioned, where we're looking at batteries, actually primarily just batteries here. So that's a battery. Those are all inside bits of batteries. I say battery probably way too much, but it's not all about lithium-ion or other types of battery technology. Oh, wait, here we go. That's a battery. Actually, it's not anymore. Yeah, so that is an exploded battery. And it gets a little bit at this project here, SafeBat, because as we start to use more and more cells in our daily lives and try to put batteries into applications that they don't really want to be in some cases, we're going to have higher and higher amounts of energy in those systems, and therefore more safety concerns. So this is some of the experiments we can do to try to understand how batteries fail and then prevent that process from happening. But yeah, it's not all about batteries, okay? Hydrogen and other things are very important as well. And this is some really nice work illustrating some of the departmental collaboration that we do from Ryan Wang's group, where they were looking at high entropy alloys for electrocatalysis. And so here you can see maybe the nanoscale and sort of atomic picture of the work that we do. And the idea here, of course, is once you've shown that you have an interesting material to test, you can then scale that up and see if it really works at sort of commercially relevant levels. We also collaborate extensively with the nature-inspired group here at UCL Chemical Engineering. And we may have seen this slide, but maybe not, actually, not so often. This is a lung-inspired fuel cell design that worked tremendously well and had really quite a nice acronym, LUCY. And so, yeah, this is another example of how, we're in the department and how electrochemistry is really touching, actually, a lot of the work that we do in chemical engineering. More stuff from us, all around hydrogen this time, because I do like hydrogen. It also has very much a role in the net zero economy that we're pushing towards. And so here we have a system where, let's go. So right on here, we've actually segmented it, and we can track and see the spatial distribution of current or temperature or whatever variable that we're interested in. And you can start to track that, as the cell is operating. You may see edge effects. You may see, commercial. Manufacturing defects. You may see all kinds of things that you wouldn't see with just an average picture. This is work that we're doing in collaboration with Johnson Matthey, where we're looking at alkaline electrolysis as an alternative to PEM electrolysis, which has expensive electrocatalysts, et cetera, et cetera. And this is a micro cell that actually just made its way to Diamond Light Source last week. I had a very successful, I'm told, beam time where they'll image the inside of that cell to see what processes are happening as it does electrochemistry. And yeah, finally, this highlights an EPSRC project that's in collaboration with Hariba and the National Physical Laboratory called Ampere, where we're looking at how to scale up PEM electrolysis in that case. Oh, and yes, and we have some videos as well. So this is a video of an optical view of an electrolysis in this case, where we have multi-phase flow. I think we'd all agree. And we can watch bubbles and slugs and various things forming here. So again, very tied in to the chemical engineering aspects. Cool. That's the EIL. How are we doing on time? Probably okay. Lots of smaller scale stuff. And since I had joined UCL, which is about 5 years ago, I've been told that we were going to move to this, or expand up to this scaled up version of life where we're going to look at real things, big things. Vehicles driving into the lab and dumping out their battery packs, and we're going to study that. And actually, that is where we are now. So this year, we opened the Advanced Repulsion Lab, which represents the next stage, I think, in electrochemical research here at UCL, where we'll be able to do a lot of the things that we were, frankly, just limited by central London in many ways in terms of what we can do. So at the Queen Elizabeth Olympic Park in East London, we'll be able to look at some of these industrial chemical engineering aspects. It's a beautiful campus. Some of you saw it yesterday, I'm pretty sure, and we've seen some of the really exciting labs and facilities that we have out at Stratford. And this is very much focused around being at the forefront of the net zero revolution. Right? So as we ramp up to 2050, we're going to need to reduce carbon emissions quite a bit. And a big component of that is going to be from the transport sector. How we get that hydrogen, for example, how we make those batteries, and then how they are deployed in vehicles are all mantras of the Advanced Repulsion Lab. We would call this the age of electrochemical power, maybe moving beyond fossil fuels, although they'll still be around and with us for a little bit longer. And I think this is evident to everyone in this room, right? We can see electric vehicles on the streets. Some of us may even own electric vehicles, right? So this is happening and only needs to accelerate in the coming decades. We're interested in all of it to some extent, and we're especially interested in electrifying things that are difficult to electrify. Aerospace, marine, for example, these are huge carbon-emitting sectors. And personal mobility, we think also there's a role for the electrification of that. My favorite part of the APL is our new dry room facility. This is something that we've been waiting for a long time, and it's crucial to making high quality batteries. Here we have a pilot line where we can really output and mimic what is done in industry. And so anything that we learn here, whether that's developing new sensors or trying to apply new battery technologies in this environment, will be directly relevant to industry and put us on a level footing with anyone else who can do this. So we're really, really quite excited about it. And finally, this year we started the Advanced Propulsion MSc. So training the next generation of engineers who will go work in these sectors. You can see lots of photos here. Sometimes they get to go on field trips. They seem happy about it. I was happy about it. It was great for me. We split this into 3 routes to try to cover and give students the choice to specialize in things that are interesting to them in this clean economy. And if you're interested, I don't know if we can take you as students again, but I wouldn't. I'm okay with it. So applications are open, and yeah, please let anybody know who might be interested. Yep. Oh, and the very last thing to say before I let you all leave is that we've done some work around hydrogen innovation. So hydrogen is going to be a huge part of our net zero future, and the landscape is incredibly confusing and difficult to follow. We started the Hydrogen Innovation Network about 2 years ago now. These are our industry partners who are involved. Some of you may work for them. They're in the room. Thank you very much for your letters of support, if so. And this was capped off with a really amazing showcase event last November, where we had ministers and heads of companies and way too many video cameras. But there'll be a video of that event and some of the things that we talked about in the near future. So look out for that.